Okay, so the next subject that we will be doing is double integrals. Oh, also some people took the quiz. They sent it in through email. I have not had a chance to grade those. So for now, you might have a 0, and I'll get to that at some point. Okay, so double integrals. So we know from Calc 1 what a single integral is, and that is, let's say, the integral over f of x dx, let's say from some bounds a to b. And the intuition behind this is that we are in 2 dimensions. Here's x, here's y, which is equal to f of x. We have some curve. We take the x-axis from A to B, and we break it up into pieces. And these are delta x's. And then this integral, well, it's approximately the sum. And let's call each one of these xi. So the sum from, let's say, I equals 1 to n, so a certain amount of these xi's, of f at some point, let's call it xi. So that is some point in this interval. Let's say this point, and we evaluate f at that point, delta x I. Right? So it's this Riemann sum, and we take n to infinity. We break these into smaller and smaller pieces. We add up the sum. That will be our integral. So in multivariable calculus, the intuition is basically the same. And again, not necessarily very important to understand. I mean, it's important to understand the intuition, but it might not be that important when we're actually integrating stuff. And these type of Riemann sums will definitely not appear on the exam. But if here is your f of x, y, and we have some box below where we're trying to integrate, then we break this up into, again, very small pieces. Now each one of these pieces has area delta, let's call it delta xi, times delta yi. So a certain width in the x direction, a certain width in your y direction. These are some areas, delta ai, let's call it. So then your double integral, a going to b, c going to d. So let's say your x is going from a to b. So here is your, this over here is x is equal to a. This is x is equal to b. And your y is going from c to d. So this point over here is y is equal to c, and this point over here is y is equal to d. Okay, so that's basically your bounds of integration. And then you have the same thing, f xi, yi. So you choose some point in these boxes, and you look at f at those points. Sorry, this is the integral. So let me do fxy dx dA, and this is equal to or approximately the sum, and then another sum, and this is I is equal to 1 to n, j is equal to 1 to n, f of let's say xi yj of delta xi delta yj. So very similar. Again, not necessary that we know exactly how these sums work, but some intuition of the fact that we're breaking up this domain into small pieces and we're summing over every small piece times the area of that piece and the height of our function. And so that gives us the area below our surface. So let's try just an actual integral. So let's say we ask for the integral from 1 to 2. And then let's say from, again, so let's go 0 to 1 of some plane. So let's say 3x plus 2y. And then we can write this in terms of dA, but you have to specify what direction you're integrating in first. So let's go dy dx. So let's try to understand what this means. So what this means, here's your x, y, and z coordinate system. You have some plane. So here's our plane. This is the plane f of xy is equal to 3x plus 2y. Now our domain is, let's say, something like this. And we're first integrating in the y direction. The dy comes first, so that's the direction that we're integrating in. And the y is going from 0 to 1. So your y is going from 0 over here. So y is equal to 0, all the way to y is equal to 1. Okay, so if you wrote the domain in 2D, here is your coordinate system, x, y. This is your domain that you're integrating over, and y is going over here from y is equal to 1 and starting at y is equal to 0. Okay, that's the first part. Then we integrate in the x direction. That's the dx. And the x direction is going from 1, which is down here, all the way to 2. So that would be x is going down here from x. Okay, so this is not the exact domain, but I'm going to change this to 0 just so that works. So x is equal to 0 all the way up here to x is equal to 2. Or in this graph, you would have here x is equal to 0 all the way to x is equal to 2. So any questions about this so far? So when we actually do this integral, we first then go in the y direction. And and we just take the antiderivative with respect to y. So this is going to be, we keep the first integral, the integral from 0 to 2. And then we put bounds for the second one. So 0 to 1, and we take the antiderivative of the function inside with respect to y. So it's going to be 3yx plus 2y squared over 2. So this 2 can disappear. Right? So that's the antiderivative of this thing with respect to y. And then we recall that there's still a dx to deal with. And that would be the antiderivative with respect to x. Any questions so far? So now we plug in our bounds. So this is going to be equal to, again, the integral from 0 to 2. And we start by plugging in our 1. And this is all for y. We're plugging all this into y because we took the derivative with respect to y. So we are going to get 3x plus 1. That's this first part. And then you need to subtract this part, but that's minus 0, right? Because you just plug in 0 into your y's and you get 0. So we get this times delta x. Any questions so far? Yeah.
You have to plug in the value before you do the second one.
Yes. Into your y coordinates in this case. Okay. So then we do the second integral, and this will be again bounds from 0 to 2. 3 over 2x squared plus x. And then when we plug in our points, we get 3 over 2 times 2 squared plus 2 minus 0. And so that's our answer. And what this means is that the the volume below our surface integrated over this domain over here is going to be this number. Okay. I think it's 8, 6. Yep. Any questions? Okay. So let's do another example. So currently our bounds of integration are constant. And we'll do a couple of examples like that. And they're also, in this case, they're going to be rectangles just to, keep things simple. We will see that you can have, let's say, triangles. Your domain can be a triangle or something with a curve, circle, stuff like that. And then things get a little bit more tricky. But so long as we're dealing with these rectangles, it's fairly straightforward what we need to do. So let's do another example. Let's say f of xy is equal to negative x squared minus y squared plus 4. So some function we've been dealing with for a while. And let's say you want to find the area in the rectangle. So let me draw, here's our x, here's our y. So let's go with the area, just a simple rectangle. So this will be x bigger or equal to 0, less than or equal to 1, y bigger or equal to 0, less than or equal to 1. Okay. And again, what this means is you have your parabola, so x, y, z. You have an upside down parabola over here. This is your f of x, y. And then we go to this domain right over here. And we want to know what is the volume of this, what is the volume of the piece below this parabola? So what is the volume over here? We can imagine. So what is this volume over here? Okay. So when we set this up, we have a double integral fxy. So let me just put that in. So negative x squared minus y squared plus 4. And then we get to decide, do we want to integrate with respect to x first or y first? Now later we'll see that this is going to get tricky, but right now, because we're in rectangular regions, so because our domain is something like this, where you have constants bounding your x and y, you can choose whatever you want. So you can say, let me integrate with respect to x first, and then integrate with respect to y. So if we're integrating with respect to x, we look at the bounds for x, and those go from 0 to 1, so 0 to 1, but also the bounds for y go from 0 to 1, so we put 0 to 1 here too. So that's how our integral looks. Any questions? So in essence, what this integral is asking, well, the first part is asking if you have some fixed y, so let's say y is fixed here, and then you start integrating with respect to x. So you take these little steps with respect to x, and you integrate over that, over this function, right? So you add up a bunch of numbers, you take this like sum, that's what an integral is, some sum, and you get the area of this thing over here. Okay, and then you do that for every y. So you go here, same thing, take the sliver, integrate with respect to y. That's basically what's happening. Okay, you're getting these little slices of integration with respect to x, and then you're doing that with respect to all the y's, so you're adding up all of these areas to get your volume. But again, taking the integral is fairly straightforward. So this is going to be, you keep the first integral 0 to 1. Now the second one is in terms of bounds. We're taking this integral with respect to x. So we get negative x cubed over 3 minus y squared x plus 4x. And then we have to remember that we're still integrating with respect to y. And then this is going to be equal to the integral from 0 to 1. We plug in our bounds into x. So we get negative 1 cubed over 3 minus y squared plus 4. And then when we plug in the zeros, we just get 0, so minus 0. And then this entire thing is now an integral with respect to y. So then when we integrate this with respect to y, we get again our bounds 0 to 1, negative 1 over 3x, sorry, y, minus y cubed over 3 plus 4y. We again plug in our bounds. So the 0, it doesn't matter, and the 1 gives us negative 1 over 3 minus 1 over 3 plus 4. And that's our integral. Some positive number tells you the volume of this surface in the domain that we mentioned, in this domain. Any questions about this? Okay, let's do a couple more examples. So let's try to find the integral over the region R of xe, xy, dA for R being the box negative 1 to 2 cross 0 to 1. Okay, so because again that your region is a box, you can choose what you want to integrate first. You know, do you want to integrate with respect to x first, or do you want to integrate with respect to y first? And it won't really matter. So this is going to be equal to some integral xe, xy, and then instead of dA, so we can recall dA is equal to dx dy, which is equal to dy dx. But the thing that we put first, we're integrating in that direction first. So let's just do this with respect to x first. So let's say d, is it probably easier to do this with respect to y first. So let's do dy. And I'm just saying that because there's just one y here and they're like these two x's. So it's just going to make it easier. So this is dy and then dx. Okay, what is this rectangle over here? Well, we can draw a picture. Here's our x, here's our y. Our x goes from negative 1 to 2. So here's negative 1 and here's 2. And our y is going from 0 down here to 1 over here. So it's something that looks like this. That's the region of integration. And so if we're going with respect to y first, we get bounds from 0 to 1 with respect to y, and then bounds from negative 1 to 2 with respect to x, xe to the xy, dy, dx. Any questions so far? Now we'll see this in more detail soon, but because again that we're in a region that's a box, yeah?
Does it usually matter if you solve for dy or dx first?
So it depends on the question. When we are dealing with these rectangles, then you can switch them without having any problem. And so then you can do it either way, and sometimes one way is easier, sometimes the other way is easier. We'll later see that if you're not dealing with a box, right, all these regions are boxes. If you don't have a box, things get a little more complicated. Yeah? Yes. It gives you, you can either think about it as the volume below this surface, right, in that region, or you can think about it as the density. So we can think about this being some density of mass. So in some areas more dense, some areas it's less dense, and the integral gives you the total density. Okay? Or mass. Any other questions? Okay. So like I said, this is going to be equal to, you can switch the order of integration. So -1 to 2, 0 to 1, x e to the xy, but now you have to switch the order of integration, dx, dy. Okay, so in these cases, we can switch these. But let's just deal with the integral that we have above. So first, we're taking this with respect to y. So you get these bounds, -1 to 2, 0 to 1. Now, when you take the antiderivative, so we want to think, what's something that if we take its derivative, we get this thing over here, right? Well, that will just be e to the xy. If I take the derivative of e to the xy with respect to y, and x comes down, which is why it's more beneficial in this case to have y first. It's just an easier antiderivative to do. So we get e to the xy, and then we still have to remember that we have this integral with respect to x, right? Any questions? So then we plug this in. So we get the integral from -1 to 2 of e to the, and we're plugging this into y, so e to the x minus 1, right? And then this entire thing is taken with respect to delta x. Okay, so now this is going to be, again, we have bounds from -1 to 2. The derivative of e to the x with respect to x is e to the x. The derivative of -1 is -x. And then we plug in, so we get e to the 2 minus 2 minus e plus 1. Okay, any questions about this? Oh, give me a second. This should be, you're plugging in -1. This is -1. And then the second one is, so this is also -1, but you're taking minus, so -1. So this is e to the 2 minus e to the -1 minus 3. Okay, any questions? Okay, so let's try to do this the second way, which is let's try to do this using our bounds to be, so now we're going with respect to, so double integral x e to the xy. Let's go dx dy, and then our bounds are going to be -1 to 2, 0 to 1. -1 to 2, 0 to 1. Okay. So because we have this x down here, let's first look at what is the integral from -1 to 2 of xe to the xy dx. So we don't really like having an x here and an xy over here. So we can, of course, use u substitution. So we can say, okay, u is equal to xy. And now du over dx is equal to y. So du is equal to y dx. But now we see, okay, so we have a y here, we have an x here. That's not exactly what we want. So instead, sorry, give me a second. Oh, okay. X. Sorry, 1 second. Okay, never mind. Anyway, so again, it is easier to do this integral going in the y direction first and then the x direction. Doing it the opposite way is a little bit more difficult, and so you can try both approaches and see what you can make out of each of them. Let's try another example. So double integral over r of x cosine squared of y dA. And now here your r is going to be -2 to 3 cross 0 to pi over 2. Okay, so in this case, it actually doesn't really matter which variable comes first. We can say that let's do this with respect to x first. So you have your dx over here, x cosine squared y. Now, if you're integrating with respect to x first, you get -2 to 3. And then we have dy. So if you integrate with respect to y, we get 0 to pi over 2. Right? Now, because that the x and the y are broken apart, you have an x here and a y here, and they're functions in terms of x and a function in terms of y, but there isn't, let's say, something like cosine of xy, right? There isn't something like that. That means that when we take this integral, we're really only, if I'm taking this integral with respect to x, I'm kind of ignoring the y part. And if I'm taking the integral with respect to y, I'm ignoring the x part. So let's just do the integral. So if you take this with respect to x, you just get an x. So you get bounds from -2 to 3, x squared cosine squared y. We have to remember that there's still an integral with respect to y. And so that's the integral from 0 to pi over 2. Right, so we see that this cosine squared of y didn't really change, right? It's kind of acting like a constant because there aren't any x's there. And then this entire thing is going to become the integral from 0 to pi over 2. 9 cosine squared y. Yep. X squared over 2, sorry. Okay, 9 over 2 cosine squared y minus, so if we put the -2 into our x squared, we get just 2 squared over 2 times cosine squared of y. And then we're still taking this with respect to y. So now when we take the antiderivative of this with respect to y, we get the bounds from 0 to pi over 2. Okay. So then we have this cosine squared y and another cosine squared y over here. Okay, so we just need to remember, and this won't really appear on tests, like remembering trig identities and stuff like that. But we just need to remember that cosine squared of y is equal to 1/2 1 plus 2 cosine of 2y. Okay, so we can plug that in. So this entire thing is going to be 1/2 9 over 2 times 1 plus cosine 2y minus 2 times 1 plus cosine 2y, and then this entire integral with respect to y. Any questions? Okay, and then when we take this, the antiderivative over here, well, this is just a Calc 1 problem, so I'm going to leave it like this. Any questions about this? So taking integrals in a rectangular region is actually fairly straightforward. You just have to take 2 integrals. Things get a little bit more complicated when we go to some more general region. So let's say instead of taking the integral in some rectangle, you're given 2 functions. So let's call them g2 of x and some other function g1 of x. And let's say that here are our bounds. So this is x is equal to a, and here's another bound, x is equal to b. And you want to know what is the volume of the function fxy above this region. So above this region over here with these specific curves, right? So our x is bounded from some amount to another amount, and our y is bounded from some amount. But our y is bounded in terms of functions. So another way of writing this exact picture is we can say our domain is the set of points xy such that, so our x is bounded from a to b, so a is less than or equal to x is less than or equal to b. And our y is bounded from g1, so g1 of x is less than or equal to y is less than or equal to g2 of x. Right? That's another way of saying the same thing. Any questions about this notation? So this is just the set of all points, the set of xy, such that our x is bounded from a to b, and our y is bounded below from g1 of x, so bounded below, and it's bounded above from g2 of x. Any questions? So if you're given this type of integral, you write it out. So first, the integral along this domain of fxy dA is going to be, and now because your x are constants, you have to put the x in this in the second integral. So this is AB, and this is the derivative with respect to x. And then you put your dx outside. So you finish with the derivative with respect to x because your x's are constants. And in the y, you put these functions with respect to g. So y goes from g1 of x to g2 of x, right? Because that's where y goes from. It goes below, it starts at g1 of x, and it goes up until g2. And pictorially, what's going on is that you start at some fixed x, so we can think about this as some fixed x, and then you take these integrals with respect to delta y. So this is a small delta y, here's another delta y, another one, right? And you take that integral by adding up these delta y's. So that's over here, your delta y's, and here's your function f of x, y, right? So you add up your delta y's over here first for some fixed x, and that gives you the area of this region. So this is some area, right? It's, you have this line, and then you get this vertical direction, some height with respect to your f, and that gives you some area. And then you keep doing this for every x. So you go to every x and you keep doing this, and you can imagine little delta x's in the x direction, and those are these over here. And what does x go? X goes from where until where does x go? It goes from x is equal to a up to x is equal to b. So that's your bounds over here. So your dy's are going from g1 to g2, and your dx's go from a until b. Any questions about this? Okay, so let's do an example like this, and then we'll talk about the other type of situation that you can have, which is that your y are some constants and your x go from some function to some other function. Okay, so here's an example. Ask you to find the double integral over the domain D of 4xy minus y cubed dA, where D is the region bounded by y is equal to the square root of x and y is equal to x cubed. Okay, and that's what they tell us. So in order to figure out what's going on here, first recommendation, make a graph of the region. So here's your x, here's your y. Now, your y is going from the square root of x, which is a function that looks like this, right? Up until this x cubed function, which is kind of flat here, so we can say something that looks like that, right? That's x cubed. So we're trying to find the area of our function in this domain, in this region right over here. Okay, so first, what is this region? Well, from where until where does x go in this region? Any suggestions? Yep. One. So yeah, x is going from 0 to x is equal to 1, right? So that's this point over here, where y is 0 and x is 0, up until this point over here where they're both 1, right? And then we integrate over these curves. So we set up the integral, and we know where we're going in our x direction. It's from 0 until 1. And we also know where we're going in our y direction. It's from the lower curve, and the lower curve is y is equal to the square root of x. So that's the square root of x down here. Up until, oh, sorry, the lower curve is x cubed, right? Because that's the curve below. That's this curve right over here. Up until the upper curve, which is the square root of x. Right? Of the function 4xy minus y cubed. Of the function 4xy minus y cubed. And now which one comes first, dx or dy? Dy, and then dx. Okay, so actually evaluating this, we get 0 to 1, x cubed, square root of x. And we're taking this derivative with respect to y. So we get 2xy squared minus y to the 4th over 4. And now we can plug in our bounds. So this is going to give us, and we still have, of course, a dx over here. And then we plug in our x's to our bounds. So this is the integral from 0 to 1. And then we get 2x times, and then the square root of x times squared. So that's just x. So 2x squared minus, and then we have the square root of x to the 4th power. So that's x squared over 4. And then we the square root of x comes first. What do you mean? You're putting this first into here and then subtracting this. Does that help? Okay, so then you subtract the x cubed, so that is 2. That is 2x times x cubed squared, which is x to the 6th power. Minus 4y, I'll just write x cubed to the 4th over 4. Okay, and now everything here is given in terms of just x. So we can take the second integral and we get bounds from 0 to 1, x cubed 2 over 3, x cubed plus x cubed over 4 times 3 minus 2x to the 8th power over 8 minus x to the 13th power over 4 times 13. When we plug in the 0, nothing happens. When we plug in the 1, we get 2 over 3 plus 1 over 12 minus 2 over 8 minus 1 over 4 times 13. Any questions about this? Okay, you mean this minus should be plus over here? X squared, yeah, here. Right. Any other questions? Okay, so again, the overall strategy was to find from where until where does our x go, from where until where does our y go, set that up in our bounds of integration. Remember to put the constants first here and then have the functions. And then you can just solve this by taking the antiderivatives. Now, a second type of situation we might get is here's x, here's y. We have some bounds, functions that bound our x. So we can say that this over here is h2 of x. This over here is h1 of x, right? So these are some bounds that bound our x, and then our y in this case goes from some constant down here. So here's some constant. Sorry, this is h of y. Y. So now our y goes from some constant, y is equal to, let's say, a, up until another constant up here, y is equal to b. Okay? And so then, and again, we're going to try to take the integral in this region. So then the integral in this case will be double integral again. We're now going to first go with respect to x, so delta x. And our x goes from, well, it goes from here, this point over here, all the way up to this point over here, right? Those are our steps in the x direction. So it goes from h1 of y, all the way up to h2 of y, right? And this is, of course, integral with respect to our function f(x,y). And then we have an integration with respect to y. And our y is going from down here, right, all the way up until here. Those are the steps in the y direction. So y goes from a all the way until b. Okay, and that's the integral in this case, and we'll do an example of this tomorrow or Wednesday.